So let's review what we've accomplished. We started with the Lagrangian, this very wonderful complex item that contained really everything about our problem. This was the kinetic term, this is the potential term, and the whole thing equals this kinetic term minus the potential term. We noticed that the potential term is only a function of r, which is why it's the central force problem. And in fact, we got even more specific than that. We actually identified it with kappa over r, which is the specific central force of the Kepler problem. So we began with, essentially we began with a more general central force Lagrangian, and then we made it this specific Lagrangian of the Kepler problem. From that we derived the equations of motion. The equations of motion, which were, and these were the equations of motion. And the critical one is this guy, the constant of the motion. And this we derive because if we look at this, we see that the Lagrangian is not dependent on phi. So we end up with this constant of the motion, which is a first-order differential equation. And then we had these two long, kind of nonlinear coupled differential equations. But we were able to show that by the virtue of the fact that the angular momentum of the system is constant, and we actually struggled to show that. We showed it in a very complex way. We were able to arbitrarily set the final equation for phi. We were able to set a theta. Theta equals pi over 2 as a constant. And this reduced everything. This discovery, the realization that the overall angular momentum is constant, allowed us to set this to a constant. And plus, using this constant of the motion equation to substitute in for places like this here, for example, and this here, setting this to constants and making these substitutions, everything got simplified to the following equations of motion. The following simpler ones, and these simpler equations of motion are actually quite tractable. This I left in a differential form because we're going to talk a lot in this lesson about this effective potential. So I should make that, so this is the V effective, and this is minus partial r of V effective. Now this is what the lesson today is bulk about. This equation of motion gets a little simplified because we lose that sine theta, which was in the denominator. And of course, this is the critical fact that we observed that made everything simple. So we end up with one critical, one-dimensional equation of motion. That's the only one that's a second-order equation that really demonstrates true acceleration. And it is an acceleration that is derivable from a potential. But there's only a physical potential plus this potential piece that is an artifact of our choice of the polar coordinate system. And that intriguing part is still a very legitimate piece of the true potential, the physical potential of, well, the physical potential. This is a fictitious, this generates fictitious forces. This generates what we would call true inertial forces. And so we want to understand what this potential is and how to understand this potential, because we're going to see effective potentials again in the Schwarzschild problem, and they're going to be extremely interesting to compare those with the classical problem. And then the next thing we did after we got the equations of motion is that we solved them, and we ended up with these two really quite beautiful expressions. I mean, this is kind of what physics is all about, right? It's really complicated math. This is probably why we jumped into physics. It's like, ooh, look at those big equations on that blackboard. I wonder what they mean. And all of a sudden, we find ourselves studying physics or mathematics straight up. So we ended up with the shape of the orbit equation, which is a really delightful expression between the radius in polar coordinates, the radial polar coordinate and the azimuthal polar coordinate. And we discovered that this mathematical expression is a conic section. This term here is the eccentricity of the conic section. And everything is driven by numbers we know, right? This is the angular momentum. This is the strength of the physical potential. This is the energy, the total energy of the particle in flyby, which is the potential plus the kinetic energy. And this is the reduced mass of the system. And so all those numbers are known based on the initial conditions. And so it's important for us to be thinking of initial conditions in terms of energy and angular momentum, which is a little different to some, the way I always think of it is, I think of myself as, okay, I'm standing on the planet, right? Here I am in the center of force. Oh, and there's like a meteor out there or a comet or a satellite or something. And it's got some position in space, r, and it's got, I'll call that r vector, and then it's got some velocity, v. And that's its initial condition. And it seems like if I know its position and velocity, I got it. I should be able to figure everything out. And that's true. But what we have to do is we have to write E equals 1/2 mv squared plus kappa over r, right? That's the potential. That's where the velocity comes in, and that's where the r vector comes in. But that only expresses that kind of blends this initial position and initial velocity, right? It kind of blends the two together to E, but I need two facts here. But these two facts are now combined to one fact, but I also have H, which is now going to be mv cross r, right? Which is going to basically be an expression of this, basically this angle, right? And so, for example, if v was straight in this direction, then h would equal 0. If z is like this, then h is somewhat maximal for a given v and r, right? Now with h and e calculated from v and r, I can now generate this equation, this equation for the shape of the orbit. And then I'm a little disappointed to say I did a bit of a bait and switch on you guys, because we did this wonderful calculation of t, reviewing some elementary calculus, but we ended up with something that was t of phi. And the whole time, I think for like 2 lessons, I've been promising phi of t. And I even made this big deal about how phi of t in Newtonian mechanics, is very different from the fact t is a parameter here, and that ultimately in the general relativity, we're going to have to do phi of some parameter lambda, which would typically be the proper time, where the proper time is the parameter. And then t would also be a function of the proper time, where this is now the parameter, and t, so Newtonian mechanics, t is the parameter, and phi is the dependent variable on t. And so I wanted to kind of demonstrate that we have the ability to calculate this function. And in some sense we do, but awkwardly, when I finally finished the calculation, we ended up with this bear, and that is actually t of phi, right? So inverting this can be done sort of in principle by, I set my value of t, and then I have an algorithm that sort of hunts through all the phi's until you match t. And there are places in physics where we've done that. Remember the equation, I think the one I remember the most is in quantum mechanics, where we studied the finite square well. Remember the finite square well, where you have a wave that scatters over a finite square well, and you actually have to match these boundary conditions of the wave function across the square well, and you end up with an equation that is sort of, I forget what they called it. I think they called it some sort of transcendental equation. I don't know why, but you couldn't just solve for it. You had to actually graph it and plot it and find the values that match these boundary conditions. So it does happen that you are looking for values, that physics problems have this issue. I'm unaware of how to invert this expression. If I was given this and told to invert it for phi, it's not obvious to me how you would do it. I suppose you could, the naive thing to do would be to take this piece here, move it over there, And then to get rid of this tangent, maybe make this tangent naked on one side, this inverse tangent, take the tangent of both sides, so you end up with like the tangent of a sine over cosine here equals a tangent of something over there. But I don't know how it's not obvious to me that you could invert this. If anybody knows how, tell me. I'd be kind of interested. I'm not some expert in all things classical mechanics. And when you prepare yourself to actually explain these things that you've known for a long time, all of a sudden, I guess I talked myself into a bit of a corner there. But anyway, we know a heck of a lot about the Kepler problem, right? So now I'd like to advance into this question of how to understand the orbits in terms of the effective potential. So I've sort of pre-wrote everything here so we can go through it step by step. But this is the force law for the radial distance. And it's the opposite of the gradient of an effective potential. So force is the opposite of the gradient of a potential. But because this potential is all only dependent on the r coordinate, that reduces to minus partial by r of the effective potential. And this is the effective potential. And it has two parts. It has the physical part, which is the actual 1 over r squared force law potential, where kappa, if kappa is less than 0, this will be an attractive force. If kappa is greater than 0, it will be a repulsive force. So we'll be thinking a little bit more about the attractive forces because we want to touch with the general theory of relativity where it's always going to be an attractive situation. This is called the centrifugal potential, and it is ultimately generates a fictitious force, and the fictitious force goes as 1 over r cubed. I should say this is a good time to show a really, really important point. The fictitious force is, it's an important point that has to do with how to identify fictitious forces. In this particular case, we see this is our so-called fictitious force, minus h squared over mu r cubed. But h, we know from our constant of motion, is given by mu r squared phi. So I'm going to make that substitution, and I get minus mu r squared phi dot squared, not phi dot squared, right, over mu r cubed. And what we get is mu squared over mu, 1 over r phi dot squared, which equals mu times phi dot squared over r, right? Let me just make sure that's right. Yeah, so the point being that this fictitious force, I'll call this the centrifugal force, where this is fugal, not centripetal. Centripetal force is a real force. The centrifugal force is this fictitious force. But notice the point is it is proportional to the mass. Whenever you have a force that is proportional to the mass, you can count on it being a so-called fictitious force. And that's really, really important, because if you look at the force of gravity in the Newtonian system, it's minus g times the mass of the gravitating body times the mass of the falling body over r squared. That force is proportional to mass. And then all of a sudden you can start thinking, whoa, is gravity? Could it be that gravity is a fictitious force of some kind? Could it be that gravity is all dependent on the coordinate system? Because we now know that this guy is derived in this equation here based entirely on the chosen coordinate system, right? If we didn't have the chosen coordinate system, if we didn't have this particular Lagrangian, right? I mean, we could have done this in the x, y, z coordinate system, which is totally this totally inertial coordinate system. Had we done it in the x, y, z coordinate system, this fictitious force wouldn't be here. And so because of that, this fictitious forces are proportional to m. But the exception would normally be gravity, which is a real force. It's a real, authentic, no-kidding force. But it's proportional to m. So in the Newtonian system, you say, well, okay, well, fictitious forces derived from the coordinate system, they're all proportional to m is sort of what ends up happening. Except gravity. Gravity is a real force that's proportional to m. But if you take seriously that, no, gravity is not a real force that's proportional to m, gravity is actually a fictitious force too, then you start walking the intellectual road towards general relativity. So that's just an important point to understand. Okay, anyway, back to this screen here. So let's imagine for a moment that we are standing here on the center planet, and we're always facing this falling particle. So wherever the particle is, we're facing it directly, right? And so from our perspective, as the little observer on the planet, we are looking out at this particle, and we're always facing it, and we're measuring our distance to it. So the distance to it is r. What would we see if we're watching it on this orbit? If we set up this arrangement and we were watching it come down on this orbit, what would we actually see in that circumstance? And what we would see is that it would come closer and closer to us, accelerating, right? And then it would suddenly start to decelerate at some point. And then at some point it hits the closest approach, right? When it gets to this spot right here, when it gets to that spot right there, that's the closest approach. And then it stops, and then it starts to go the other way. And it starts to accelerate the other way until it reaches some uniform velocity and then just proceeds to infinity away from us. So by looking at this, what it seems to us is happening is that at some point there is a force acting on this particle that is accelerating it toward us, and then suddenly there's a force that's slowing it down, and then there's a force that's pushing it away, and then finally there's no force at all. So the point of this is that there's only one physical force, right? That's this derived from this potential, this r squared force, and that force is attractive. So the force that's pulling it toward us can ultimately be attributed to that physical force. But this force that ends up pushing it away, right? This force that kind of keeps it at a distance. I mean, it doesn't completely close its distance. It actually turns around. Is that fictitious force? That fictitious force, which grows much faster as the distance shrinks, right? As the distance gets small enough, this fictitious force could in principle become relatively large. And it's that fictitious force which apparently keeps it at bay. Now, we know what's really going on. We really know what's going on is that it's kind of just avoiding us and moving along. But if you were to look at it just from this coordinate alone, it would appear as though some force is slowing it down and pushing it away. So that's another way of thinking about these fictitious forces. And the reason I'm going through this is because this picture in R is really one of the ways we are going to be studying how to characterize these orbits using the effective potential. And to do that, we plot the effective potential versus radius. And here's a typical chart. Effective potential is measured in energy, so we're going to make effective potential in the vertical, and the radial distance is in r. Now, we'll start with a condition where the angular momentum equals 0, right? And in that case, the effective potential equals just the real potential, k over r. And if we plot that, it's going to look something like this, right? Well, because it's minus k over r, right? Because it's minus, let's see, well, it's not minus k over r. It's k over r, but k is going to be less than 0. So I need to write k is less than 0, right? Because we want an attractive force. So the effective potential is going to look like this. And what we're going to do is we're going to set this energy so that the energy equals 0, right? That's 0 of energy. So that at infinite distance, the effective potential energy is 0. So what does this actually mean? This means that if I'm positioned, if I'm stationary relative to the center of the coordinate system, so that's where r equals 0, And you'll notice that phi and theta are completely suppressed. So when I think of, say, a point at a certain radial distance r, in this case with 0 energy, so that point is plotted at a point with 0 energy at a certain radial distance, we could call that r sub 0. In a way, we can think of that point for r, but all different values of phi and all different values of theta. It kind of represents a sphere of possible points. But if we choose one value of theta, and we choose one value of phi for this particular problem, we can imagine particles being held at 0 energy total, zero total energy at all of these different places. And what does that actually mean to have 0 energy in this circumstance? Well, your total energy is equal to the kinetic energy plus the potential energy. And in this case, if that was to equal 0, then if the total energy equals 0, then the kinetic energy is going to equal the opposite of the potential energy. And the potential energy is this value right here, right? It's a plot of this potential. So the kinetic energy is going to be this little gap, right? It's going to be that little gap, and it's going to be positive. And that gives you a total energy of 0. Notice that at a total energy of 0, you have some kinetic energy, and you have a negative potential energy in this circumstance. The circumstance where h equals 0, which means the only potential, the only part of the potential is this part, right? This part goes away, right? So if you're farther away, you have less and less kinetic energy because there's more and more potential energy, or the potential energy approaches 0, and it does so at a rate that's very dependent on this k, right? The stronger that k is, the slower it approaches 0. Now, what's important to understand, too, is that the force associated with this potential is minus the gradient of the potential, right? So the gradient of the potential here, say here, the gradient is a positive slope. So the force is going to be negative the value of this slope. So say that slope was alpha, the force is going to be minus alpha. And therefore the force is attractive because the unit vector r is always considered to be in the positive direction. So a negative force is going to be attractive, or towards the center. So this potential here, as long as kappa is negative, everywhere there is some force, but the force becomes extremely weak at large distance because this slope, this gradient, becomes less and less. So that's how to interpret this piece of the potential. Now, likewise, you could come in with a large energy, a significant energy. That could be, say, the energy of a particle. And when I put a point here, what I'm basically saying is a particle at this radius, I'll call that one R1, with this amount of energy, total, E1. I know its potential energy is over here, but this graph here is just really, it's energy versus, so energy could be E or potential energy. This blue line is just the potential curve, right? That's this value. But if I talk about a test particle in this system, I say the test particle is at a certain R1 at a certain energy, and then there's my dot. So right away I can tell you what's the force on that test particle. I just take the slope of the potential curve at that point and take the opposite sign of that, and it's attractive. So I know what force is acting on the particle. And but the energy is conserved, right? So I know that the particle under the influence of this force will always stay on a line of E1. The question is, what will its radius be? And if the particle is motionless, well, if the particle was motionless, then it would have zero kinetic energy, and it would be at this location on the potential curve. But it would still have a force, and energy is conserved, and all of its energy is just the potential energy, right? So E would equal V, which would be some negative value. It would have a negative total energy, which is acceptable. It's acceptable. And that force would start pulling it this way. And at this point, say, now it would have E, which is still it's still some constant value. It's the same value as it was when the particle was here. But now that E is the kinetic energy plus the potential energy, but the potential energy is now lower, which means it's even more negative. So now we have the kinetic energy equals that total energy minus the potential energy. And of course, that potential energy is T plus K, I'll call it R2, right? And but K is less than 0, right? So again, the total energy, wait a minute. The kinetic energy is the total energy, E minus V, which is E. Hold on. What? This is so easy. The total energy is E plus TV. The kinetic energy is E minus V. V is going to be increasingly negative as particle moves towards the center of the center of symmetry, the attraction point. So you can see that kinetic energy builds up. And in this case, it's just going to go all the way until it enters the center until it actually hits the center of the system. But what's interesting here is if you take this seriously, the force becomes infinite, right? Because remember, as R becomes 0, this force gets stronger and stronger and stronger. So as long as you have this mathematical idealization of a point source of the force and a point particle, the force will become infinite. So, you know, in reality, you imagine that there's a limit to how close you can get to 0 because the gravitating body has some radial extension, right? And therefore, somewhere way down here is the lowest potential you can get, and basically the particle is just falling right onto the surface of the gravitating body. So that is how to interpret this graph when h equals 0. The interesting thing happens is when h is no longer 0. And this is what happens when h does not equal 0, right? So here we have h is greater than 0. And notice everything changes at this point. The first thing that changes is that no longer do we have this infinite level of attraction. As soon as there's any value of h at all, any angular momentum at all, you're going to have this piece here, because as r gets really, really small, this term is going to become arbitrarily large and will always defeat this term. And remember, we're considering attractive forces, so we have k less than 0, right? So this is negative, this is always going to be positive, and so ultimately, you will always have this turnaround here in the middle where the potential energy just takes this arbitrarily large climb. So you no longer have this infinite dip. So that's really interesting. And what that means is that with any angular momentum, you can never reach the center of symmetry. And that's the way we interpret that is clearly what that means is you always have to do at least a flyby orbit. Well, you will usually do this flyby orbit. There are a lot more hyperbolic orbits and elliptical orbits. So, and that's why so as long as you have some angular momentum, you will avoid the center of symmetry. The case that we just studied was this h equals 0 case, where you literally have no angular momentum and you just fall right into the center of symmetry. But as soon as you develop any angular momentum at all, you fly away from the center of symmetry, and in this case, you could imagine it some hyperbola like that, getting pulled around very tightly, but you never reach r equals 0. And so in this circumstance, we imagine a particle. Well, first we could imagine a particle let's imagine a particle of some positive energy. Yeah, some positive energy like this. So this is a particle that at R0 has an energy equal to E0. So we know that its force, the force is going to be the slope of this line here, the opposite sign of the slope of that line. That slope is positive, so the opposite of that sign will be negative, so the force will be in the R direction, and R will tend to get smaller from R0. and this particle will always keep the same energy, and so will always be at this energetic level, but R will change with time. And as R changes, the partitioning of the total energy between the kinetic energy and the potential energy changes, because the potential energy follows this curve here. The potential energy is following this curve. So the potential energy is getting increasingly negative, so the kinetic energy gets increasingly positive. And that is how the particle accelerates towards the center. What happens is as soon as it passes this point right here, now the force is actually zero, apparently, at one point, and that actually is going to be, from the perspective of these orbits, that point is going to be the point of closest approach, right? Because at that point, the second derivative actually is zero. The force appears to be zero right there, and the value of R is stationary. So that happens right when this becomes level, at the bottom of this trough. And then the force changes direction and becomes repulsive. And it actually becomes arbitrarily repulsive. But the force peaks out, as far as the particle is concerned, right at the energetic barrier. It hits this angular momentum wall. And at that point, the particle actually... at that point, that's where the particle turns around. What did I just say? I just said the particle turned around. Yeah, okay, I've got this totally wrong. At this point here, that's where the particle starts to appear to decelerate, right? That's where the particle starts to appear to decelerate. And then by the time it reaches this point, that's where it turns around. So this is the turnaround point. This is the point where the particle actually starts to appear to decelerate. So this point here of closest approach is when you've actually hit that angular momentum barrier. Where the particle starts to slow down is somewhere out here, right? Somewhere out here, where here it just appears to be freely falling and getting faster and faster and faster. Then at some point you realize, whoa, it's actually not getting faster anymore. It's actually the radial distance. It's actually slowing down. So somewhere in here is where this point is. Okay, so that's how to interpret this thing. On this chart, you only see the idea of the radial motion. You can interpret what the force is for the particle, because you've got the shape of this potential. But notice this is the total effective potential. It includes this angular momentum barrier right here. And this chart shows up in classical electrodynamics. It shows up in atomic physics a lot. In particular, collisions of atoms all have these effective potential barriers. There are bound states in quantum mechanics that live in this well, and then there's scattering states that fly this way across the well at different energies. And the zero momentum in quantum mechanics, you really do have a zero angular momentum state. So you have all these bound states down here as well. It's just a really fascinating subject. But this, so this will all, so the more angular momentum you have, the larger the effect of this barrier will be. This barrier will get a little farther out, and it'll be a little bit shallower, and it's just a very dramatic dependence on H. Now, if your total energy is negative, that means you're below this line. That means if you say you start right there. You can never be down here, right? Because you always have at this radial distance r, just to be put there requires the investment of a certain amount of potential energy. So this whole space is unavailable to a classical particle, right? And I say a classical particle because in quantum mechanics you do have some what we call barrier penetration that will allow particles to enter into places that are classically forbidden. But if your particle starting there, then your entire universe you can never get closer to the center of attraction than the angular momentum barrier. You can never get farther away than the potential barrier, which basically is saying that the attractive part of the potential, that means the physical potential, restricts how far away you can get. but the angular momentum part of the potential restricts how close you can get. And of course, that is reflecting these elliptical orbits. The perfectly circular orbit is this orbit right here, right? If your particle starts with that energy at that radius, it'll never get farther and it'll never get closer. And so that orbit would actually be just some sort of circular orbit. Well, not some sort of, it would be a circular orbit around, which is just a limiting case with eccentricity 0. So this potential is really, really important. Now what we're going to see with the Schwarzschild geometry is this. We're going to see something that looks very similar to this. Really, really similar. All the physics is going to be the same. And then all of a sudden, we've got that. That's what's going to be so dramatic about the Schwarzschild potentials. All of a sudden, there's this, you can have, if you're at a high enough energy, right, meaning you've got enough speed, and remember, the shape of this curve is always determined by the angular momentum, right? The more angular momentum, the more sort of dramatic this curve is. And each angular momentum has its own potential curve, right? And just as each mass of the sun or mass of a star or source of the Coulomb potential, the attractive potential, whatever 1/r² potential it is, that determines the shape of this curve. But the curve will always have the same characteristics. At infinity, it'll always be 0, and towards the center of attraction, it'll always blast up to infinity in the classical potential. In the Schwarzschild dynamics, what we're going to discover is that it suddenly has another turnaround and it plummets to 0 all the time. And so if you start, say here, with enough energy, you can actually go over the top of the angular momentum barrier and hit the center of the potential, despite the fact that these orbits in the classical world would never do that, right? So that means another possible orbit in the Schwarzschild geometry is going to be scoop, and it gets sucked in, right? That is possible in the Schwarzschild geometry. It's completely impossible in the classical geometry. Also, in the Schwarzschild geometry, you could imagine being right here, right? You can imagine being at the top of that potential. The force there is flat, right? It's still flat. There's no force pulling you in or pushing you out. So in principle, you could have an infinite orbit at the top of that potential. So at the bottom of the negative potential well puts you out here. But then there's the possibility of another circular orbit riding the crest of this potential. It's an unstable orbit, right? Because if you just go a little bit too far away, then the force tends to push you away again. And if you get a little bit too close, the force will suck you in. So there's an unstable orbit right there. The classic circular orbit is right here. At this energy, at that energy, and at that distance, you'll have a circular orbit even in the Schwarzschild system. But you'll also have this other circular orbit possibly in the middle, but it's an unstable one. Okay, but we're going to develop that more closely in our upcoming lectures. Now, the point of all this classical review was to compare the two. So, and I think we've accomplished that for today. So I think on our next lecture, we'll be able to get back to the Schwarzschild geometry. All right, talk to you then.